In this case, I think I gave the example. If I look at the back data, that I treated as the same, which may have been a bad idea. But yeah, you can do it on the training. Well, you can't do it. Well, yeah, you can't do it on the training if you built the full tree. So you need some dev set to get it out. It's not compelling. So in this case, yeah, I mean, you can see that what we did here is, you know, we had less areas that we pruned right here, so we went in and pruned, and you just keep on kind of going through. And then if you want to prune even the other cases, you just pick the sets where consider all leaves, take the min error, and take that one, something silly like that. Okay, and then costing, it's not really relevant, but just that you have different error functions for false positive and false negative, so you reflect that in your entropy calculation or your clustering. Not super compelling. We'll go through the midterm example, but does anyone have any burning questions as they've gone through their notes, maybe separately from me going through their notes if they want to get clarification on? No? Okay. All right. So this was, hopefully, we'll see, I don't know, but this was the point at which I felt you guys were confused. And I went to the whiteboard, but hopefully if we go through this now, maybe it'll make more sense. So the idea here was that we started with coins and just the idea that for a given coin, we can sit there and flip it and get a sequence of flips, and we know it's a Bernoulli. That how do we go about estimating the parameters that it's a Bernoulli based on what we've observed? And this, obviously extends to naive Bayes and everything else. That we're going to observe some documents and what's the probability? How do we set the parameters such that they reflect the probability of these documents occurring? That's the way you should think about it. So it's the probability of the data given our parameters is what we end up modeling. So what we did here was Bernoulli. So there's some parameter, and basically every time, or this is for a single flip, right? So if we observe the heads, that's the probability of observing heads, and the probability of observing tails is not a head, and 1 minus that probability. Very straightforward. And we want to find an estimate for mu. So we're going to do maximum likelihood first. So we have n events. This is obviously looks like naive Bayes eventually. So the assumption here is that we have n events. They're IID. So it's just the product of the independent events. We substitute that in. So this was our likelihood function. We have a product of this occurring n times. And effectively, you can sum up that if I say this is h, then this is the number of times the h. Yeah. It's just a product of the individual cases. So we want to select a model that maximizes that likelihood. That's our likelihood function. And the way we do this is take the log just because it's easier to work with, because sums are easier. And if we take the log of that function, it ends up being number of heads times the log of mu plus, hey, all these nodding now, it's fantastic. Should always teach twice. So take the derivative, set it to 0, and solve for the parameter we're interested in. And it ends up, which everyone knows before we started, it's the number of heads divided by the number of times I flipped. Shocking result. Binomial is just a different, yeah.
The maximum likelihood estimate, is that the probability of the given mu or the mu itself? Like, what is the
maximum likelihood estimate?
Yeah.
So it's an estimate of mu such that it will give me the maximum likelihood of the data occurring.
Right. Okay. Yeah.
So it's a maximum likelihood estimate of a parameter. So yeah, the value of that parameter means that I will maximize the likelihood of the data. Binomial, it's just the probability of h heads given n flips. The reason this is relevant is when we did the multinomial naive Bayes that looks like this, that really you weren't computing the probability of a word occurring. we're really computing the probability of this word occurring this many times in a document, if you really think about it for a while. So binomial, I didn't put it there, so it's learning guarantees, you don't care right now. This you kind of care, or you should know. So Bayesian parameter estimation, so the idea here is that just my observations, I don't believe actually reflect reality. You know, there's people, I don't know if people have ever heard the Bayesian frequentist argument, I'm sure I mentioned it briefly, but Bayesians are right, but it's hard to justify because basically it's just a way of encoding crap you pull out of the sky. You know? That so the example here is if you observe 5 coin flips that are all heads, it's almost impossible that a coin has that much more mass on one side, so you would put some prior over your estimates. And even though we talk about the beta here, which we'll get to, the way you should think about priors for discrete variables is you're basically adding pseudocounts. So for the multinomial night Bayes in your homework, you basically pretend that you have an example of that word, even though you've never seen it. So basically what you're doing is you're taking the entire vocabulary and appending it, you know, just adding a one if it didn't occur before. That's really all you're doing is you're fake appending, and that's really all this. The math isn't doing that, but that's really all you think about intuitively. So the math here is you have some prior over your hypotheses, and so therefore I'm actually computing the probability of the hypothesis given the data, which is a little bit reversed, Bayesian. This is my maximum likelihood times my prior over my data. You never care about the data, so it's you know, related to this. For many probability distributions or parameterized distributions that people are familiar with, like Bernoulli, multinomial, there's conjugate priors. The math works out really nice because the products end up being additions and exponents, things like that. So for the Bernoulli or binomial, you have the beta, and the beta, if you really look at it, is the number of fake heads. It's the number of like pseudo counts of heads is what you're essentially doing. So your expectation looks a lot like the probability of fake head occurring, and your variance looks somewhat similar to the other case. Yeah. So yeah, it's not important about the shape. This is not anything I could really ask you in a meaningful way. All I could really ask you, frankly, is what's the conjugate pair? Something silly like that, which isn't a good question, but it's I think a fair question. If I was to ask you something about betas or something about, probably not Dirichlet's, but anyway.
But you just said you weren't going to ask this.
I'm not going to.
Okay.
But I could. That's what I'm saying. I think it's fair.
What do you mean by the conjugate pair?
Oh, so a conjugate. There you go. Conjugate prior. Yeah. So the conjugate. So there's a pair for a given distribution. There's usually a conjugate distribution that's your prior, and the reason you want the form that way is just that when you look at the beta here, so you kind of need to put slides together, but the fact that it ends up being a mu to the h times I don't remember, a to the h, they add together, right? So you end up that this is literally our pseudo example, where because we have this conjugate prior, the conjugate prior is the mathematical way of expressing these kind of pseudo counts being added. So the beta is the conjugate prior for the Bernoulli or the binomial, and you end up with that it looks like heads plus my fake heads over tails plus my fake tails, right? And the reason, it's just when you take the product of them, because the functional form looks like this. It looks like this is your maximum likelihood, this is your prior. So when you stick it together, they just look nice. They're convenient mathematically. It's more for a math.
Not a great justification, but
Is it always
Yeah.
the beta function is the conjugate prior?
For a Bernoulli or for a binomial? So a multinomial, this would be the case, right? Because a beta is only parameterized by a number of pseudo heads and a number of pseudo tails.
Right.
If I was rolling a die, I need some other prior, right? In that case, it's the Dirichlet. And the Dirichlet is effectively a pseudo count added to every class. So for the multinomial, what you'll often have, so actually in your homework, when you added a 1 to everything,
Yeah.
that was a Dirichlet where you're just adding 1 to everything.
Gotcha.
It's called the Dirichlet, right? But if we were to do the math, it looks like it's the same functional form. The math looks pretty.
How do you spell that?
D-I-R-C-H.
Dirichlet.
Yeah.
Okay.
And that's probably not how he pronounced it.
It's
I once word. Yeah, but he was German or something. So it's like, how do Germans pronounce it?
Really angry sounding.
Okay.
Okay.
It's true.
I go to Germany a lot, and I will agree. Every time I'm on the train, the first time I'm like, it sounds so angry. But I've been, no, it's because I've been trained. I don't know about World War II. Anyway. Yeah. Oh, and Germans do not find Nazi Germans funny at all.
Did you find that out the hard way?
I found it the hard way. Oh boy.
Mommy, can we know the joke?
Yeah, I'll take it. Oh, well. Okay, I'll very briefly. So there's a Berlin machine learning group, bigger than the Seattle one at Amazon, and they name all their projects that they work on after rivers in Germany. Okay, and they have like 50 projects. And so I said at some point, like, well, what are you gonna do when you run out of rivers? Are you gonna next another? And they were like,
Poland.
funny. Yeah. They just died, and I was like, oh, that was a good joke.